dear students, last class we discussed about some of the introductory terms in thermodynamics. Today we are going to discuss about thermodynamic properties. We are going to discuss about some of the important thermodynamic properties. One among them is internal energy. Internal energy. Now what is internal energy? Internal energy is the energy inside a system. Internal energy is the energy inside a system. If you consider this as our system, then the energy inside this system is known as internal energy. So internal energy is the energy inside a system or intrinsic to a system. Internal energy is represented by U. Okay. Now second question, how this system is getting energy. So question is how this system is getting energy, how this internal energy is formed inside a system. To explain how this internal energy is forming inside a system, I am considering a system and the system consists of a cylinder. With a frictionless movable piston. And this cylinder is filled with any gas, let it be HCl gas. This cylinder is filled with HCl gas. Consider this as our system. So our system consists of HCl gas. Okay, our system consists of a cylinder filled with HCl gas and a frictionless movable piston. A movable frictionless piston is attached to the cylinder. Now, if you consider a single HCl gas, okay, this HCl gas can show, a single HCl gas molecule can show 4 types of motions. First one is rotational motion. Second one is vibrational motion. Third one is translation motion. Okay, fourth one kinetic motion. Fifth one electronic motion. So there are different types of motion. A single HCl molecule can show different types of movements. What is mean by rotational motion? Consider one HCl molecule. In HCl molecule, there are 2 types of atom. One is an H atom, and second one is a Cl atom. Right? Cl and H atoms. Now, these 2 atoms are attached to form HCl molecule. Okay. Now, these 2 atoms, H and Cl atom in HCl molecule, they always keeps on rotation. They will rotate. Keeps on rotation. That means they always rotate. H atom will rotate in one direction, Cl atom will rotate in another direction. So in an HCl molecule, both the atoms will rotate. As a result of their rotation motion, they have an energy, and that energy is known as rotational energy. Due to rotation of H atom and Cl atom in HCl molecule, okay, due to that motion, they have rotational energy. Let the rotational energy be E rotation. Okay. Both the atoms will rotate. This H atom will rotate here. It will rotate here. Cl atom will rotate here. That means they keeps on rotating. As a result, they possess rotational energy. I think it's clear. Now, this HCl molecule can also show vibrational energy. What is vibration energy? This HCl molecule, they will vibrate from their mean position. For example, if this is H atom and this one is Cl atom, they will vibrate in their bond. They will vibrate from their mean position. So they will vibrate. So when this vibrate, it will form like this. Again, contraction, expansion, contraction, expansion. So it will vibrate from their mean position. Both the atoms will vibrate from their mean position. As a result of this vibration, an energy will be produced, and that energy is known as vibrational energy. So a single HCl molecule can show rotational energy. A single HCl molecule can show vibrational energy. A single HCl molecule, if you consider a single HCl molecule, it can move. It can move, and the energy required for movement, or translation for the zigzag motion is known as translation energy, right? So a single HCl molecule possesses three forms of energy: rotational energy, vibrational energy, translation energy, due to three different motions. Both the atoms in an HCl molecule can vibrate in their mean position. As a result, vibrational energy is produced. Both the atoms can rotate. As a result, rotational energy is produced. A single HCl molecule can move they can move. As a result, translation energy is produced. So, a single HCl molecule possesses rotational energy, vibrational energy, translation energy. Now, if you consider a system, we are not considering a single molecule, we are considering bulk of molecule, because in thermodynamics, we usually consider bulk system. So, in thermodynamics, we are not concerned about a single molecule, we are taking large number of HCl molecule here. We are taking HCl gas. HCl gas consists of infinite number of HCl molecule. Infinite number of HCl molecule, right? Infinite number of HCl molecule. For example, if you consider this as our system, it consists of infinite number of water molecule. Large number of water molecule, right? Likewise, if you consider HCl system, this HCl system consists of large number of HCl molecule. A single HCl molecule can possess rotational energy, vibrational energy, translation energy. That means, if you consider this system, there are large number of HCl molecule. Each and everyone can show these three energy. So, each and every molecule can show these energy. So, energy for a single HCl molecule is energy rotation plus energy vibration plus energy translation. This is the energy of single molecule. If you are taking a large number of molecule, each and every one has these three forms of energy. So they possess energy. As a result, a system will have energy, and that energy is known as internal energy. Energy inside a system is known as internal energy. Now, how this internal energy is produced in a system? If you consider a bulk system, a bulk thermodynamic system, there are large number of molecules. A single molecule can possess rotational energy, vibrational energy, translation energy, kinetic energy, electronic energy. There are different forms of energy. A single molecule can show these forms of energy. That means in a bulk system, having large number of molecule, okay, each and everyone can show this much of energy. Each and everyone can show these three energy, or there are 5 forms of energy. You have to study these three. Each and every molecule can show these three energies. That means a bulk system consists of large molecule. So the system is having an internal energy. That is internal energy. That energy is known as internal energy. Energy inside a system. It is represented by U. I think it's clear. Now, internal energy is a state function. Internal energy is a state function, which we have already discussed in our introductory topic. State function. What does mean by state function? Functions which depends on state independent of path. Functions which depends on initial state and final state independent of path are known as state function. Internal energy is a state function. State function, and it is an extensive property. Extensive property. And this topic is also discussed in our introductory part. Extensive property. Property which depends on amount of substance. So, internal energy is a state function and an extensive property. State function means which depends on initial and final state. Extensive property means which depends on amount of substance. So, internal energy is a state function and an extensive property. I think it's clear. Now, if a system, consider a cylinder filled with a gas, and the cylinder is attached with having a frictionless movable piston. Let the system be filled with any gas. Okay. Now, Now let the internal energy of the system, let the internal energy of the system be U1. Let it be U1. So the internal energy of the system is U1. Let it be U1. Now, an internal energy of a system can be changed only by two methods. Internal energy of a system is changed, or it can be changed only by two methods, either by supplying heat energy or by supplying work energy. By supplying these two energy, we can change the internal energy of a system. For example, if I am heating the system, if I am supplying heat energy, that means if I am heating the system, obviously what happens when we supply heat energy? The molecule, each and every molecule will absorb that heat energy. As a result, their rotation energy will increase, vibration energy will increase, their translation energy will increase. As a result, internal energy will increase. Right? So when you supply heat energy, each and every molecule will absorb that heat energy. As a result, their rotation energy increases, vibrational energy increases, their translation energy needed to move, their translation energy increases. As a result, internal energy of the system increases. Let that internal energy, okay, it will increase. Okay, now when we supply work means if I am pushing this piston, work is a form of energy. If I am pushing this piston downwards, that means I am supplying energy to the system. I am doing work to the system means I am doing work on the system means I am supplying energy, because work is a form of energy. Right? That means I am giving energy to the system. Work is a form of, okay, work is done on the system. That means I am supplying, work is a form of energy. That means I am supplying energy to the system. So when we supply energy to the system, again, rotation energy of the molecule increases, vibration energy of the molecule increases, translation energy of the molecule increases. As a result, internal energy increases. Let the internal energy be U2. Let the new internal energy be the U2. So once more, let the internal energy of a system be U1. Let the initial internal energy be U1. Now, I am supplying heat energy. When we supply heat energy, that molecules inside that system will absorb heat energy, so that their rotational energy increases, vibrational energy increases, translation energy increases. As a result, their internal energy increases. Now, when we do work, when work is done on the system, that means I am pushing this piston. Pushing means I am doing some work on the system. So that work is also a form of energy. So I am supplying energy. Again, rotational energy, vibrational energy, translation energy of the molecule increases. As a result, internal energy increases. Let the new internal energy be U2. So we can write U2 is equal to U1 plus Q plus W. When we supply heat energy and work energy to the initial internal energy, we got U2, final internal energy. So I am taking this U1 here. So U2 minus U1 is equal to Q plus W. What is U2 minus U1? Delta U. Delta U is equal to Q plus W. Delta U is change in internal energy. U2 minus U1 means delta U, that is change in internal energy. So change in internal energy is equal to change in internal energy. Change in internal energy. Change in internal energy is equal to Q plus W, heat and work. I think it's clear till here. So what is internal energy? Internal energy is the energy inside or intrinsic to a system. It is represented by U. You can change internal energy of a system either by supplying heat energy or doing work. Work is a form of energy. It means you are supplying a form of energy, right? Either by supplying heat energy or doing work. So when we supply heat energy or work energy, both are energies. That means you are supplying energies. As a result, rotational energy, vibration energy, translation energy of the molecule increases. So internal energy increases to U2. So we can write U2. The new internal energy is equal to initial internal energy plus Q plus W. I'm taking U1 here. So U2 minus U1 is equal to Q plus W. Delta U is equal to Q plus W. Change in internal energy is equal to heat plus W. So these are the two methods. These are the only methods to increase internal energy. These are the two methods. Either by doing heat or either by supplying heat or by doing work, we can increase the internal energy of a system. Okay, I think it's clear till here. Moving on to next topic. Moving on to next topic. First law of thermodynamics. In thermodynamics, there are four important laws. First one is first law of thermodynamics. Second one is second law of thermodynamics. Third one is third law of thermodynamics. And fourth and final one is zeroth law of thermodynamics. First law, second law, third law, and zeroth law. First law, second law, third law, and zeroth law. So, first law of thermodynamics. Now, what is first law of thermodynamics? First law of thermodynamics states that energy can neither be created nor be destroyed. Energy can neither be created nor be destroyed. Or, it is also stated like this, or total energy in the universe is always constant. That means energy can neither be created nor be destroyed. Energy cannot be created or cannot be destroyed. That means energy is always constant in this universe, right? Energy is not, we cannot create energy, like we cannot create energy and we cannot destroy energy. That means energy inside this universe is always constant. So second law is, and total energy in the universe is always constant. Okay. Now mathematically, first law is represented like this. Mathematically, first law is delta U is equal to Q plus W. This is the mathematical equation for first law of thermodynamics. Delta U is equal to Q plus W. Why we are using this equation to explain first law of thermodynamics, or why this is the mathematical form of first law of thermodynamics. This equation is considered as the mathematical equation for first law of thermodynamics. Why this is considered as the mathematical equation for first law of thermodynamics? Consider a cylinder. Consider a cylinder with a frictionless movable piston. And the cylinder is filled with a gas. Let the internal energy inside this cylinder be U1. I am supplying heat energy and I am doing work energy. Right, I am supplying heat energy and I am doing work energy. That means its internal energy will change to U2. So, U2 minus U1 is equal to, U2 is equal to, the new internal energy is equal to U1 plus Q plus W. I am taking U1 to the side. So, U2 minus U1 is equal to Q plus W. What is U2 minus U1? It is delta U. Delta U is equal to Q plus W. Now, this equation states that here, heat energy and work energy is converted to internal energy. Heat energy and work energy, it is converted to internal energy. That means, energy can neither be created nor be destroyed. It can be transferred from one form to another. This equation shows that here, heat energy and work energy. Heat energy and work energy. These two forms of energy, these two energies are converted to internal energy. Right. So, energy can neither be created nor be destroyed, but we can transfer one form of energy to another form. Heat energy and work energy is converted to internal energy. So, this is the importance of this equation. That's why this equation is considered as the mathematical form of first law of thermodynamics. So, what is first law of thermodynamics? Energy can neither be created nor be destroyed. That means energy in this universe is always constant. These are the two statements of first law of thermodynamics. Mathematical equation is delta U is equal to Q plus W. Delta U is change in internal energy. What is delta U? Change in internal energy. Q, heat, W work. Okay, so moving on to next topic. Moving on to next topic, sign convention. Now what does mean by sign convention? Sign convention means if a system is absorbing or releasing energy, if a system is absorbing or releasing energy, those energies are represented by different signs. For example, if heat absorbed by a system, if heat is absorbed, if a system is absorbing heat, that means heat absorbed by the system. Heat absorbed by the system is always represented by plus Q. So plus Q indicate, that means plus Q indicate heat is absorbed by the system. At the same time, if heat energy is released by the system, heat energy released by the system, it is taken as minus Q. So minus Q indicates energy is released by the system. Plus Q indicates energy is absorbed by the system. Okay, so sign convention help us to find out whether energy is released or absorbed. So in the case of heat energy, if heat energy is absorbed by a system, then it is represented by plus Q. At the same time, heat energy released by the system is taken as minus Q. Now, work. If work is done on the system, work done on the system, if we are doing some work on the system, that means I am pushing this piston, that means I am doing work on the system. Work done on the system, let it be on, let it be by, okay. Work done on the system is taken as plus W because we are supplying work energy. So work energy done on the system, that is plus W. At the same time, work done by the system. If the system is pushing this, piston upwards, that means if the system is pushing this piston upwards, that means the system is doing work to push the piston. Work done by the system is taken as minus Q. So these are the sign convention. Once more, heat absorbed by a system. For example, consider a system. Let this be the system. If the system is absorbing heat energy, then that heat energy is plus Q. If a system is releasing heat energy, then that heat energy is minus Q. Okay. So work done on the system is taken as, I am doing work on the system. I am pushing the piston downwards. That means I am doing work on the system. So work done on the system is taken as plus W, and work done by the system is the system is pushing the, if this system is pushing this piston upwards, that means system is doing work to push that upwards. So it is taken as minus Q. Okay. Now, work done on the system. This work is known as compression work. This work is compression work because we are applying work on the system. Let this be system. This is our system. So we are applying work on the system. That means its volume decreases. When we apply work on the system, this piston will move downwards. When we apply work, the piston will move downwards so that volume decreases. So work done on the system is compression work. At the same time, if system is doing work to raise the piston, if system is doing work to raise the piston, that means volume increases. So work done by the system is expansion work. So these are the four important sign convention. Heat absorbed by the system, plus Q. Heat released by a system, minus Q. Work done on the system, plus Q work done by the system minus Q. Work done on the system is compression work and work done by the system is expansion work. I think it's clear till here. Moving on to next topic. So moving on to next topic, work. What is work? Work is a form of energy. It's a form of energy. Now, work usually depends on path. It is independent of initial state and final state. Work usually depends on path. It's independent of initial and final state. So work is a path function. This topic is already discussed in our introductory part. So work is a path function. And all forms of energies are extensive in nature. All forms of energies are extensive in nature. Since work is a form of energy, work is an extensive property. So work is path function and an extensive property. Work can be classified into two types, irreversible works and reversible work. Works can be classified into two types, irreversible work and reversible work. Now what is meant by reversible work? Work which take place infinitesimally slow. So work which take place very slowly. Infinitesimally slow means very slowly. Work which take place infinitesimally very slow, those works are known as reversible work. Now what are irreversible work? Work which take place rapidly. Okay, they are known as irreversible work. So I'll start with irreversible work. So first one, irreversible work. So irreversible work. Now what are irreversible work? Irreversible work means work which take place rapidly in a single step. In a single step. If a work take place in a single step, then those works are rapid works. That means they proceed in a rapidly. So those works are known as irreversible work. So works which take place rapidly in a single step are known as irreversible work. Now we are going to derive an equation for irreversible work. So we are going to derive an equation for irreversible work. To derive that, first we can consider a system. Consider a system filled with ideal gas. Okay, so consider a cylinder with a frictionless movable piston. And this cylinder is filled with an ideal gas. Let the initial volume of this cylinder, this is our system, okay, this is our system. Let the initial volume be V1. Let the initial volume of ideal gas, or let the initial volume of the system be V1. Initial volume. Now, let the pressure inside the system, that is pressure due to ideal gas, be internal pressure. Let it be PINT, internal pressure. Let the pressure inside this system, that is pressure of ideal gas, let it be P internal. Now pressure external, that is pressure outside this system, external pressure. So pressure external or external pressure, let it be PEXT. Let it just be, okay, so pressure external or external pressure be PEXT. Okay, so consider a cylinder with a frictionless movable piston, and the system is filled with ideal gas. Let the initial volume be V1, volume of ideal gas be V1, and pressure inside this system, that is pressure of ideal gas, be P internal. Now external pressure, that is pressure outside this system, let the external pressure be P external. Now consider, if pressure external is very much greater than internal pressure, if external pressure is very much greater than internal pressure, if external pressure is greater, it is very much greater than internal pressure, the piston will move downwards. Why this piston is moving downward? Because external pressure is greater. So this external pressure will induce a force. It will push this piston downwards. Since this pressure is more, external pressure is more, it will push the piston downward. As a result, the piston move downwards. in a single step rapidly. As a result, since external pressure is very much greater than internal pressure, the external pressure will push the piston downwards. As a result, this piston will move rapidly in a single step. It will move rapidly in a single step. In a single step, it will move downwards. I think it's clear. Let the new volume, this is the new volume, let the new volume be V2, final volume. Okay, so since external pressure is greater than internal pressure, the external pressure will push the piston downwards. So this piston moves downwards in a single step rapidly. Rapidly in a single step it will move downwards. So please listen that point, rapidly in a single step. It will move downwards rapidly in a single step. I think it's clear. Now, what is force? What is force? What is pressure? Before that, what is pressure? Pressure is force acting per unit area. Force acting per unit area is pressure. Right. So what is force? Force is equal to pressure into area. So force is equal to pressure into area. Now, due to external pressure, this piston is moving downwards. So due to external pressure, a force is applied here. This external pressure is inducing a force here. As a result, this piston moved downwards. So this force developed due to external pressure. So here pressure is external. Here a force is developed. Here the force develops due to this external pressure. This external pressure is inducing a force here. As a result, this piston moved downwards. So this pressure, so force, let it be force is equal to pressure. Pressure is external, not internal pressure. It is due to that force developed here is due to external pressure. So external pressure into area. Now what is the area? Here the piston moved from here, from this point to this point. Right. Let the distance covered by the piston be L. Let this be the distance covered by the piston. This is the distance covered by the piston. Okay. Now, let this be the area covered by the piston. Let this be the area covered by the piston. I think it's clear. For example, if you consider this as the piston. Initially the piston was here. Now the piston moved till here. Right. So this is the distance covered by the piston. This distance covered by the piston. And this portion is the area. This is the area covered by the piston. This is the area covered by the piston. A. Okay, okay. Now, so area is A. Area covered by the piston. Area, and this is the length or distance covered by the piston. Distance, length covered by the piston. So instead of area, you can write A. So force is equal to P external into A. I think it is clear till here. Now, what is work? What is work? Work is equal to force into distance. Force into distance or force into displacement. That is work. Force into displacement. Here force is pressure external into area. This is force. And distance is L. This is the distance covered by the piston, and that is L. So instead of distance you can write L. I think it's clear till here. Now, what is length into area? What is L into A? What is length into area? What is length into area? What is length into area? Length into area is volume. V-O-L-U-M. Volume, right? Length into area is volume. So instead of A into L, you can write W is equal to work. Work, that is work, W. You can write W. W is equal to, work is W. W is equal to P external into volume. Because area into length is volume. I think it's clear till here. So W is equal to P external into volume. I think it's clear till here. So I'm going to rub this part. So is it clear till here? Just due to external pressure, a force is developed. Here external pressure is greater than internal pressure. So due to external pressure, a force is developed here. As a result of that force, the piston move downwards. So pressure is equal to force acting per unit area. Force is equal to pressure into area. So here force developed is due to external pressure. So instead of pressure, we can write external pressure into area A. This is the area covered by the piston A. And this is the length covered by the piston L. Let the new volume, final volume be V2. So force is equal to external pressure into area. Now what is, so this is force is equal to external pressure into area. I think it's clear till here. Now what is work? Force into distance or displacement. Force is external pressure into area and distance or displacement is length L. This is the distance covered. So work is equal to P external into A into L. Now what is A into L? What is length into area? It's volume. Length into area is volume. So instead of A into L, you can write volume. So work W, let it be W. W is equal to P external into volume. I think it's clear till here. I'm going to rub this part. Okay. So work W is equal to P external into volume. Right. Now we cannot write here volume because there are two volume terms, V1 and V2. There are two volume terms, initial volume V1 and final volume V2. So instead of volume, you can write W is equal to my P external into volume change, because here volume is not constant. Here volume is changing. V1 changes to V2. V1 is the initial volume, V2 is the final volume. So we cannot write here, we cannot write volume here because volume is not constant. Volume is changing. So instead of volume, I am writing volume change. I think it's clear. So W is equal to P external into volume change. So W is equal to P external into, what is volume change? Final volume minus initial volume. Volume change means volume change or change in volume. Change in volume or volume change. You can write change in volume. Change in volume is V2 minus V1. Final volume minus initial volume. Always change is calculated by like this, final minus initial. Always change is calculated by subtracting initial from final. Final minus initial is change. So change in volume is V2 minus V1. So instead of volume change, we can write V2 minus V1. So W is equal to P external into V2 minus V1. I think it's clear till here. Now, which is greater, V1 or V2? Which is greater? V2 is less than V1. We know that from this, we can write that. Okay. Now, here from this figure, we can find that V2 is greater than, V1 is greater than V2. V2 is from here to here. From this part to this part. And V1 is from here to here. So here V2 is less than V1. So when we subtract V1 from V2, V2 is lesser and V1 is greater. So W is equal to P external into V2 minus V1, that is delta V, change in volume. Delta V, change in volume is delta V. V2 minus V1 is delta V, and I am putting a minus here. Why I am putting a minus here? Because V2 is lesser than V1. When we subtract V1 from V2, we will get a negative value. For example, if V2 is 3 and V1 is 5, what is V2 minus V1? You will get minus value, right? That's why I am putting a minus here. So W is equal to P external into minus delta V. I think it's clear till here. I think it's clear till here. Now one more step remaining. So I am rubbing this part. One more step remaining. Now, final equation to calculate irreversible work is W equal to P external into V2 minus V1 is minus delta V, right? And I am putting a minus in front of this. I am putting a minus. Okay. I am putting a minus just before P external. Why I am putting a minus here? What type of work is this? This is a compression work, right? This is a compression work. Volume decreases. So it's a compression work. In sign convention, we have already discussed compression works are always positive. Work done on the system, that is compression work, it will be equal to plus W. Work, for compression work is always positive, but when we neglect to put here minus here, we will get W is equal to minus P external into minus delta V. Okay, since it's a compression work will not be equal to negative work. We will not get work as negative. This is compression work. We will not get work a negative value, because in compression work is positive. So in order to make work positive, we are putting a minus here. So minus and minus, it will become plus. Okay, so equation to calculate irreversible work is minus P external into delta V. This is the equation to calculate irreversible work. I don't know whether it's clear or not. Last step is, here we got W is equal to P external into V2 minus V1, right? Volume change, that is V2 minus V1. Since V2 is less than V1, we will get a minus value, right? V2 minus V1 is delta V, we will get a minus value. So we will get W is equal to P external into minus delta V. Now the problem is, this is a compression work, right? Volume decreases, that means a compression work. For compression work value should be positive. Okay, value of work is positive. But here, when we calculate V2 minus V1, we will get negative value. In order to make work positive, I am putting a minus here. Minus, you will get plus value. So equation will be equal to W is equal to minus P external into delta V. Delta V is negative. No need to write that negative, because when you subtract, you will always get a negative value, because you are subtracting a bigger value from a smaller value. So you will get a negative value. So no need to put this negative. Tries to study this equation. W is equal to minus P external into delta V. This is the equation to calculate irreversible work. Equation to calculate irreversible work. W is equal to minus P external into delta V. This is the equation to calculate irreversible work. What are irreversible work? Work which take place rapidly in a single step. In a single step, if that piston move downwards in a single step, then that work is irreversible work. And equation to calculate irreversible work is W is equal to minus P external into delta V. I think it's clear. Why we put a negative here? To make W value positive. Always compression works are positive. We consider a compression work, so work value should be positive. In order to make work value positive, we are putting a minus here. I think it's clear till here. Okay, so first one is irreversible work. Moving on to next work, that is reversible work.